And we don't often call it exploding or use the E word. We tend to call it rapid disassembly. You can make a cell up to 550 watt hours per kilogram, which is getting into that sweet spot where it really, really is of interest for the aerospace.
Hello, I'm Ben Sampson, editor of Aerospace Testing International, the world's leading magazine dedicated to the application of testing, evaluation, and inspection in the aerospace industry. I'd like to welcome you to this episode of Testing Talk. Our interview today is with Ulrik Grape, President of European Operations at US-based battery technology company 24M. Engineers have been assessing and testing lithium-ion batteries for use in aviation for a while now, prompting lots of debates about energy densities, cell decay, thermal runaway, safety, and the like. Despite the debates, we are now in a period where battery electric aircraft are being tested and soon will be in operation. This isn't even to mention drones, which are becoming increasingly widespread and where lithium-ion batteries are already used widely. 24M and companies like it have pragmatic technology for batteries that will be useful for aviation applications. But what I found most interesting during my chat with Ulrik is that he's seen batteries roll out in electronics, automotive sectors, and now sees it happening in aerospace. He therefore has lots of insights worth hearing. So now it's time for the main event. Wherever you are and whatever you're doing, get comfortable and listen to my interview with Ulrik from 24M. Do you want to start first by telling me a little bit about 24M, and then we'll go into some of the failures associated with batteries?
Sure. Yeah. 24M is a technology company based in Boston in Massachusetts. It was a spin-off from MIT back in 2010, so it's a 15-year company now. It's really focused on developing technologies and introducing them into the lithium-ion battery space. We have about a little bit under 200 employees, as I said, based in Boston, but we also have a pilot line in Thailand. And then we, of course, are actively pursuing and working with OEMs in different spaces, both, certainly automotive, which is, of course, the big industry today, but also other applications such as portable electronics. And we do have some activities also in the aerospace sector as well.
One of the things I've seen in my capacity as editor of a aerospace testing magazine is videos and footage of lithium-ion batteries exploding and catching fire, and people testing them to that point of destruction. So can you just tell me a little bit about, having known so much about them, how does that happen in a lithium-ion battery? What are the kind of primary failure mechanisms of it? What's the technology and engineering behind it? What's happening?
Yeah, we don't often call it exploding or use the E word. We tend to call it rapid disassembly when that happens. But kidding aside, no, it's a serious topic, of course, and safety is paramount because you're dealing with a lot of energy that's stored in a compact space, right? And I can give you an example, right? For example, if you think about the battery that started off with the lithium-ion battery industry back in the early 1990s, it had, since then, that same cell has almost fivefold increased its capacity. And it hasn't changed its volumetric volume, so you can see how much more energy is being pushed into the devices. Now, failure mechanisms of lithium batteries, it depends, on what they get exposed for. They certainly, you can have, they get more stressed if you charge and discharge them very fast. They get also stressed, if you will, when they are exposed to low temperatures. Then there's other factors that could be related to the manufacturing or the assembly of the cells. If you're not exact enough in terms of how you're building the cells. One of the things that's happened is, of course, we've increased the energy density over all this time. And some of that is all about tightening the tolerances that are in the cells. So you're having less and less overlap space or security space, if you will. And that's also, an issue in terms of if you get any contaminations in the cell that are kind of inevitable in some regards from the production side, you can also create what we call an internal short circuit. But there are other failure mechanisms. It could be poor wiring or poor connections between the cells, etc. So there are kind of multiple possible failures. But I think we're seeing more and more that the cause of the more recent events are related more to that we're seeing an internal short circuit of the cells. And that's, of course, very difficult to stop from happening from the outside. And you really have to attack it from the inside, or the design of the cell, the internal design of the cell. And that's where we come in.
So it sounds to me as well that there's a quality issue within manufacturing here and of lithium-ion cells that's crucial as well. Is that correct?
Well, I wouldn't. I mean, the cell manufacturers today are doing a fantastic job, but as I said, as you're tightening the tolerances, your margins for error are getting tighter and tighter. And there, if something goes wrong, at the same time, you have a manufacturing process, and there could be some metal contamination that occurs during the process that can lodge itself inside the cell, and then over time that can evolve into what happens is that what we call something called lithium dendrite growth inside of the cells. So that's actually, it's kind of a mossy growth that occurs inside the cell. It can occur naturally. It does occur naturally as you charge and discharge the cells. Mm-hmm. It's impacted by low temperature, or if you're charging or discharging it at very high rates, meaning that if you're trying to charge a cell in 5-10 minutes, it's stressful for it. And if you keep doing it, then these dendrites will grow. The dendrite can also grow if you have a contamination, for example, from stainless steel or something like that inside the cell. The dendrite will grow through there, and if it punctures the separator that's in between the positive and the negative in the cell, or the anode and the cathode, as we call them, then you can have an internal short circuit. And when that internal short circuit happens, that's very instantaneous. We're talking about milliseconds that happens. And then it's hard. Then it's almost impossible to stop it from the outside. The only way people are attacking that from the outside is to try and avoid a propagation, so meaning from cell to cell. From our side, from 24M side, we think that we need to go back in and look at the design of the cell, and that's where we've developed this impervio separator that has some unique characteristics that I can explain to your listeners if you're interested in that.
I'm fascinated to hear. I mean, it's interesting to hear you talk about the way that this can happen. It would be great to get to impervio in a minute. But I wanted to ask first, I mean, you guys are working, work a lot with drones, right? Are there points of a drone flight, or indeed a larger aircraft, at certain points there's more energy needed, more power needed? I'm thinking during takeoff and landing. Those stresses on a battery. I mean, is a battery more likely to fail at those times because of the draw on it?
Yeah, I mean, clearly, I'm not a drone expert, but it's clear from our work with some of them that, when the drone is lifting off, it's using the most energy. It's very stressful because you need a lot of what we call power at that point. And then when it's actually in its flight, it's kind of a very stable, not stressful situation. It's just normal. But then when it descends again, it's also being subjected to these very high power inside. And of course, in those situations, that's where you can have this buildup of dendrite growth over time. And that can be one of the failure mechanisms. Now, I'm not saying that necessarily the failure mechanism of some of the incidents we've seen, but that's certainly what's becoming more and more prevalent. We see that in the vehicle situations we've seen, and also in stationary storage applications where this is the main cause of the safety incident, the thermal runaway.
Thermal runaway. Okay, now that's the key term. I hear that. You hear that with batteries quite a lot, right? And you've done well to get almost 10 minutes in without using that term, I think. But I mean, that's this kind of propagation of one cell failing and then another cell failing and another cell failing, right?
Well, a thermal runaway is actually the cell itself that's taking off. That you're not stopping what's going on inside. It's really a runaway. It's once you have that internal short circuit, then the energy is released in milliseconds, and you will have then this very explosive fire. There, I used the E word, but that, of course, what they're trying to do with hindering the propagation is that it won't spread from cell to cell. So you try and build up kind of barriers. So there are different solutions that people will use to try and create barriers so that it won't go from cell to cell. But we believe you need to fundamentally go inside the cell and try and stop it inside the cell before it ever happens, because once an internal short circuit happens, there's nothing you can really do from the outside to stop what's going on.
And this is Impervio, right?
So the Impervio, yeah. So the Impervio it's a unique. What we do is it's a treatment of the separator. So this barrier between the anode and the cathode, or the negative and the positive, inside the battery. And what happens is when these dendrites grow, so then when they approach or get to the separator, there's a function that's happening, that it's being turned away and dissolved, so that the dendrites get turned away and do not continue to grow. I mean, they will continue to grow, but they're moved away. The separator, the Impervio separator, also then we have the ability to monitor what's going on inside through a connection out of the cell. So we can monitor what's going on, so we can see what's happening. So ultimately, in the last instance, though, even though the Impervio is working very well, let's say that, over time something did occur over time anyway, and you get to an event, or you get closer to an event, we have the ability, together with what we call the battery management system of the battery, to shut down the cell before it gets into the thermal runaway situation. Well, it has basically three functions. It hinders the dendrite growth, it monitors, and ultimately it can shut it down so that we don't have the incidents in the worst scenarios incident.
So this is a proprietary technology for 24M, right?
Yes, it's something that we've developed ourselves, and we have the intellectual property and the patents for this. Yes.
Okay, and it sounds like a fail-safe system. Aerospace aviation loves a fail-safe system, right?
They do.
Yeah. So, I mean, are there similar systems? I mean, you mentioned you can design around it, but I mean, are there similar systems? And, would a battery in a drone or an aircraft at the moment, would it have these kind of fail-safe systems, to stop?
No, I mean, we are not in a product today. I mean, this technology was developed basically year and a half, 2 years ago, and so we are now providing samples of the Impervio separator, or cells that we've made with the Impervio separator, to different potential customers that are testing and evaluating this technology. And the other thing I can add is that we have provided this Impervio separator to customers that have then tested it, and there is no performance impact of using the Impervio separator. So it is a true drop-in replacement. So people are evaluating it. Of course, a lot of it's automotive. It takes a long time. About the aerospace. It takes a long time to get approved. So we're in that process and having a great interest for it.
Good stuff. Okay, we talk a little bit about testing and standards in aerospace. If you're a drone manufacturer now making a lithium, making a drone which is powered by lithium-ion batteries, what are the standards? Do you know what standards you have to meet? I mean, how would they typically be tested?
I'm not an expert on this, so on the testing parameters, etc. I was trying to check just before our call on that, and I'll follow up to you if I do get the right information. What I can tell you is that, for example, there are UL standards, there are IEC standards for testing of lithium batteries that are quite extensive. And I know that also, for example, in the automotive space, that's also takes safety extremely seriously. Perhaps not quite at the level of aerospace, for understandable reasons, but certainly they take it very, very seriously. They also perform a lot of these tests and have their own testing procedures that they want to do that can be particular for each individual car company. That they have specific ways they want to do a test. For example, it could be, this what we call a nail penetration test, which is supposed to simulate an internal short circuit, for example. So there are very specific, rigorous ways of testing your cells that we also try and do, and to make sure that that our cells are performing according to what I just told you.
So do you work with the regulators? Do you work with FAA and other kind of EASA and people with your battery technology?
We know. I think if at this juncture we work through
Oh,
through our customers, if you will, that in this case.
okay. So what's your main product? Semi-solid battery, right?
So semi-solid battery is a electrode technology that was the original technology that was spun out of MIT back in 2010. And basically what it is that we have the ability to make the electrodes, so the ones that are actually holding the energy, we can make them in a thicker paste, as you would call it, which means that it can be it can be more packaging efficient with the technologies that we apply, or the chemistries that we apply inside. It also has the advantage that because the way we do it, it can cut down on the capex and the opex on the production lines of making cells. It is a technology that we've licensed to, for example, Kyocera in Japan, and Kyocera has been manufacturing it since 2020 in Japan, and they've been using it for their stationary energy storage applications for residential energy storage. I know that one of your questions was around this was, can this be applied towards the automotive space, aerospace? And I think that the energy density of the technology is not attractive enough for aerospace as such. Because you need to get up to some very high energy densities in order to put it into an aircraft, because it needs to be light, right?
mm. Yeah.
Our other technologies, the impervio separator we talked about, is absolutely interesting for aerospace. We've also developed kind of in parallel to the impervio, we developed something called an eternalite electrolyte. So that's the liquid you put into a battery that enables the ions, if you will, to go back and forth between the anode and the cathode. And the eternalite we actually originally developed it for lithium metal-based batteries, which is the ones that give you the lightest lithium cells available. And we could demonstrate that we could make a cell up to 550 watt hours per kilogram, which is better than anything that exists today, which is getting into that sweet spot where it really, really is of interest for the aerospace. We did take it then also to, because of its performance, we said, okay, let's try this with some of the other lithium chemistries that also have a high energy density, maybe not at the same level as that, but still potentially attractive. And we could see that it gave very, very high rate performance. That means it can provide very fast charge and discharge, which is, of course, very interesting for drones, etc., for takeoffs, because as we call them, the C rates are very, very aggressive at that point, without any of these dendrite growth occurring. The other thing we saw also, or have demonstrated, is that this eternalite electrolyte works well down to minus 40 degrees Celsius, where we can basically pull upwards of 80% of the energy out of the cell, which again is something that would be very attractive for the aerospace, because they, of course, more than perhaps automotive, etc., get exposed to some of these lower temperatures. Well, we all know what's up when we're up flying, right? The outside temperature, etc. So it's very attractive for that. And then finally is the one that I also mentioned, our third technology, which is this electrode to pack technology. Please watch this space. Within the next couple of weeks, we're going to make an announcement of it, but it's a very efficient packaging solution that would also be very attractive, I think, or we're convinced that it would be very attractive for the aviation industry as well.
Ulrik, you mentioned there the extremes of temperature. I mean, aerospace is all about extremes. There's some really big extremes there. From your perspective as a battery developer, I mean, what do you see as the biggest challenge, really, of putting this technology into aircraft? I mean, is it these extremes that batteries have to go through? Is it the power demands that are placed on them? Or is it all of it? I mean, maybe comparing it to automotive, comparing it to cars, that use case.
No, I mean, I would like to say all of it, right? But I mean, I think it's, safety is paramount, right? We saw some issues some years ago with a battery issues that they had in a certain aircraft, but and then you see that there are drone failures, and of course with drone failures, if they fail when they're up in the air, then you don't have the same, somebody falling down and can cause a fire. So safety is paramount, right? And so that's critical, I think, also for aviation. I mean, I worked a year in the airline industry back in the mid '80s, and I knew that what the pilots were most scared about was any kind of electrical fire, right? But so I understand the the criticality of safety for aviation. Of course, that but so that's kind of paramount. But I still think that this ability to provide these very high charge and discharge rate, because to take this aircraft, whatever it is, a drone or a smaller electric aircraft off the ground requires a lot of energy in a short period of time. So to the degree you've got a technology such as our Eternal Light that can provide that without damaging the battery, that's a huge point. And then, of course, airplanes are out in extreme temperatures as well. So the low temperature performance of it is highly attractive. And we can come back to ETOP next week.
Yeah, sure. So, I mean, what do you see? What do you hope the impact of 24M's technology will be on the aerospace sector? I mean, I mean, obviously, adoption is great. You mentioned before you're working a lot with drones. Do you just see you helping increase densities and range, making things safer all the time? I mean, is that the goal that you're working to?
Yeah, I think with our technology, as I mentioned, we could work with the lithium metal, right? Which would definitely, to the degree you can adopt it into in aircraft, we can provide both a safe and high rate performance technology that provides that light battery, right? That's critical for aircraft, right?
Where do you think we are with regarding the rollout of battery technology into aircraft? I mean, do you still look at claims, or did you ever look at claims of manufacturers, developers of aircraft, and think batteries and they're never going to fulfill that brief? This never going to reach that range. Outlandish claims about what they'd be able to do. Do you think there's been a kind of adjustment of what battery technology is capable of, or you talk
Yeah,
about?
absolutely. Yeah, absolutely. I think you can kind of parallel the path that I've been on, right? When I started out, it was back in the mid '90s, right? It was portable electronics. The lithium batteries came in to enable the GSM phones and the color screens and the faster and faster processors that have been critical to the portable electronics. Back then, we thought, hey, maybe the holy grail was automotive, but we were like, can we get there cost wise? I mean, the technology was there in that sense, but yeah, we're there. I mean, we're seeing now, in the country that I live in, Norway, you have 90% of new car sales are electric vehicles, and in other countries it's starting to approach 50-50, right? And now, I think the same thing for aviation. Yeah, I mean, maybe we won't, maybe it'll be a long stretch to get to the really, really big aircraft, but for more of the shorter flights, and of course drones, they're already electric, and the batteries are getting better and better and lighter, so they're enabling that, and that's becoming a booming industry, multi-billion industry that continues to grow. And like I said, for the shorter aircraft, I see electrification happening. Yeah. So I'm very excited about it. It's fantastic to watch it grow.
Can I ask you one final question?
Sure.
And this wasn't on our list, but it is about the sustainability of batteries. Are you happy that the area that you work in? I sound like an environmentalist, like I'm on the attack. But the battery chemistries that you're using, do you think they're better, actually fundamentally better for the environment than oil and gas? Do you think are we solving a problem with CO2 and making another problem in the future, or do you think we're going to be okay with batteries?
No, I mean it's a great question, Ben. I mean, I just saw a statistic or a new report recently that says, that completely debunks this factor of saying that batteries are negative to the CO2 versus the fuel cell cars or the combustion engine vehicles. Sorry. It's the numbers are that basically after 17,000 kilometers, it's the electric vehicles outperform in terms of CO2 emissions. Now, of course, the lithium batteries have had cobalt in them. When they started off, they were lithium cobalt oxide, so cobalt's not so nice for various reasons, the toxicity, but also where it's being mined, etc. But the cells that we're seeing now with the increasing energy density are removing much of the cobalt and concentrating on manganese and nickel that are not of the same caliber in that regard. So we keep pushing, we keep pushing, and also the manufacturing process, etc., get better and better. So no, I think I may be convinced because I've been 30 years in the industry, but I think the data all around is saying that batteries are the future, and everything is going electric. And I'm not saying that oil and gas is going away, but it's clear to me that the batteries are the critical element to doing this. And it's and I to take on my European hat, I think it's just critical that we also keep on building that here in Europe for both strategic, commercial, innovation, and sustainability reasons. So.
Okay, great. It's interesting. Thank you, Ulrik. Thank you for letting me quiz you and getting my stealth environment question in at the end there as well.
No.
So, the Impervia and the rest of the product range. If anyone's interested, just go to your website, right?
Please, contact us. We're open for business, and we definitely want to connect with anyone in the aerospace business.
I hope you enjoyed this conversation with Ulrik Grape, President of European Operations at 24M. Join us again next month for another episode of Testing Talk from ATI. In the meantime, stay in touch with us at aerospace-testing-international.com or on LinkedIn and via this podcast. That's it from me. Until next time.